Now, looking at problem 2, starting with the fully 3D unsteady Reynolds transport equation, show that it reduces to W dot in equals to M dot times HT out, where the subscript T means total enthalpy out minus total enthalpy in for a compressor with steady 1D flow with a single engine outlet. There's a couple more assumptions that you need for this one. And change in potential energy are neglectable, so equals 0. The work, so they said the work out is equal to 0, so there's no work out. And then it's adiabatic, so Q equals 0, which means adiabatic. Okay, so now that we've done all of these things, what I'm gonna do is I'm gonna start writing the general equation over here. So I'm gonna go to the supplemental data pack and I'm just gonna copy it down. Let me write here that this is homework 2, homework number 2, and I'll also give a little bit of a sketch over here. So it's important to not lose focus on what we're sketching or what we're analyzing. And we're basically analyzing a control volume. And it's very generic on purpose because then it's very versatile. So we're gonna have a component made up of the storage, and you'll see this term on the Reynolds transport theorem. So this one is going to be dV with the bar, which means volume. And then you're going to have a little patch of surface here, indicated by dA. So now let's get to work. We have the big D x over dt. This is an immaterial derivative. It has a component that is more than just a derivative. I'll show it to you right here. If you go to lesson 18, this is the component that it has. It has a convective term. So it's not just a normal derivative. It behaves in a certain way, and that's why we just have a table for values that we can substitute based on the analysis that we're doing, which I'll talk to you about in a second. So now we have the derivative with respect to time of a triple integral. And this triple integral is x, which is our generic value, times rho, which is a symbol for the density inside of this control volume, all at every little bit of the control volume. And we're going to integrate this over the control volume. Then we're going to add, and we're going to add two integrals, 1 and 2. And we're going to have a little bit of an x here, a rho, and then we're going to have the v because we're talking about something that comes in and out, so that has some sort of relative movement to the control volume. And then we have our differential a, and this is integrated over a. So this is our general form. Now they asked us, if you remember here, they asked us for an energy balance. So for an energy balance, I don't know who changed the color. I didn't change it. For an energy balance, this is what we get. So we have that the big X is equal to E, while the small x is equal to E divided by M, which is just a specific energy, which if you remember, it's equal to the static enthalpy plus V squared over 2, right? Plus GZ. Okay. So now we have what the small x is. What is dx over dt? Dx over big dt, the immaterial derivative, is going to be equal to the q dot minus the w dot. Now these are the net heat and work exchanges. So you write this as q dot in minus q dot out. And then you have minus open parenthesis q dot w dot out minus w dot in. Now, the one thing that I find a little bit confusing is the signs with this, because you know in thermodynamics the work out is negative. In our case, the work out will be negative, the work in is positive. I said it backwards, so it's confusing because in thermodynamics the work out of a system is positive, and yet in this formula the work out is negative. But just look at the data pack and make sure that you have the proper signs. Work out, work in has to be positive, which will be if you distribute the negative sign. So now that we have this, we can substitute that for dx dt, but we'll do that later. Let's first simplify everything. So this will cancel because the changes in PE is equal to 0, okay? Then we said that there is no work out. It's a compressor. So actually, I'll do the sketch of a compressor, and it'll be like this. There'll be the compressor here. There will be a control volume, which is what we're trying to analyze. There will be a shaft coming in. So we can say that there's work dot in, and then we have the m dot in, and here we have the m dot out. And let's see, what else do I have to do for this? Let me check. You want to check on your engine components to see if I wrote everything. Yes, I did. So that's good. So since it's a compressor, it has no work out. It doesn't produce any work. So I can say that the work out term goes away because the work out is equal to 0 for compressors. Okay, well now that that work out is 0, I also know that it's adiabatic, so I can get rid of both of the Q's, 0 and 0, 0 and 0, because it's adiabatic. That's why I said we needed more assumptions. That's adiabatic. Okay, so now we can plug things back in. Now remember that this also cancels out because we are talking about steady flow. Steady flow. Okay, so now what are we going to do? Well, that goes away, and then we are left with the other term, and we can substitute dx dt. That's not going to be 0 because it's an immaterial derivative. It has different properties, so it won't just be 0 even though the flow is steady. So we have the work in, which is positive, the work in, and it still has a dot, is equal to what? Well, it's equal to, I'm going to rewrite that integral as the integral on area 1 of x, I lost my subdata pack, here it is, of, right here, of x times rho times the v dot times n, closing that, times dA. And this is going to be 1. It's going to be 1. But first, actually, what I want to do is let me put what x is. So x is going to be h plus v2, v squared, over 2. That's our x. Then we have our rho. And then we have our v vector dotted with our normal vector to the surface, to the control volume's surface, all over that surface. Well, not over, integrated over that surface. So now I can split this into two parts. I'll rewrite the work in here, and I can say that this is over A1, that this is H1 plus V1 squared over 2, rho 1, and then we have V1 dot N, where N is the normal vector to the surface, so it really doesn't distinguish between in and out, because it always points out. And then we have the other term. So we have plus a term that is the same but changes the subscripts, because it's for the outside part of the control volume. And we're assuming these are the only two parts in the control volume. Divided by 2. I don't know why I put 1. I wanted to put 2, both. Here, 2 and 2. And then I want to put my rho, 2. And then I want to put my V2, 2, dot N. And then I want to put my D, my dA here. Okay, so now what I'm going to say is that we can take these things out. And the reason why we can take them out of the integral, why would you take something out of an integral? Well, if it's a constant. And we are saying that they are constant throughout this whole surface because of the 1D flow assumption. And we can say the same about this. 1D flow. So now I can just rewrite this as W dot in equals to H1 plus V1 squared over 2. All of this is multiplied by a density rho 1 times V1. This is the interesting part. Now the V1 becomes negative V1 because the V1 pointed inside and the vector, the normal vector to the surface, pointed outside. Then over this A1 we have dA, and then we have a plus, and then we have, actually, we have the same thing, but for the exit. So that's going to be our total enthalpy, which I'll define later, H sub 2 plus V sub 2 squared over 2. Then we close that. And then we have a rho 2. Then we have a v. It actually doesn't have a negative sign here because v2 points in the same direction as the normal vector. And then we have a double integral. I don't know why these integral signs come out so bad. Of dA over A2. So now that we have this, we can rewrite this as, let's define this as, I don't know if this is a good color. Probably not yellow. Never ends up well. So this one we'll say is the H total 1, the total enthalpy at 1, and this is the total enthalpy at 2. So now we can say that the rate of work inside is really equal to HT1 times, well, let me write this, the one with the 2 subscripts first, because they're positive. HT2 times rho 2, did I put a subscript on the V here? No. Times rho 2 times V2 times A2, I hope you recognize that term. Then we have minus HT1 times rho 1 times V1 times A1. So now that we have that, we realize that this is m dot 2, and this is m dot 1. Now, for CISO, single in, single out, m dot 2 is equal to m dot 1, so we'll just write it as m dot. And doing that, this equation becomes w dot in equals 2 m dot times ht2 minus ht1, and then we close that. Now, they were asking us for w dot times m dot, because we could make it that specific work, but they were asking us for this. So we'll keep that, and we'll box the answer here. That's one answer, and that's the other answer. All right, make sure you document your work, and then you can turn it in.